Alright, so today we're talking about properties of polynomial functions of a higher degree. So we've talked about polynomial functions before. Hopefully we all have an understanding of what a polynomial function is and what we're looking for in a polynomial function. Today we're going to look at properties of those polynomial functions. We want to understand how to find the degree, the end behavior, possible real zeros, possible number of terms, and the intercepts of a polynomial. A lot of this stuff you've done before. By a lot of it, I mean all of it technically. A lot of it we've actually done already this year. So let's get right to it. Well, first, let's find polynomial functions, and let's have a better understanding of zeros. Okay, so what are zeros of a polynomial function? Well, zeros are the solutions. These are both real zeros, so those are x-intercepts. Another word for these is roots as well. So there's going to be many correct answers to a polynomial function that has these given zeros. What does it mean if I have a 0 that's x equals 0? That means that I had a factor that was x minus 0, which we don't normally write, but this will hopefully help us understand a little better. And if I have x equals 2 as a 0, then I also had a factor x minus 2 equals 0. That's how I ended up with x equals 0 and x minus 2, or I'm sorry, and x equals 2. So if I put these together, I can say I have some polynomial function, so I'll use function notation, and x minus 0, I can just write that as x, and then I can write this as x minus 2. We can multiply this out if we want. I did not specify here, so you don't have to. But this would be one correct answer where I'd have those two values as zeros. Just to show you what do I mean by there's many correct answers? Well, for instance, I can put any power I want on this x and it'll still have the same zeros. So if I did, for instance, f of x equals x to the 5th times x minus 2. X to the 5th will still give me 0 as a 0, and then I still have the x minus 2. I could also add a power to the x minus 2, so let's make that maybe cubed. So I have x to the 5th times x minus 2 quantity cubed. This just means that the 2 has a multiplicity of 3. Here the 0 has a multiplicity of 5. You can see in your note packet what I mean by multiplicity. So at the top in the definitions for this section, I talk about multiplicity. It's how often a 0 occurs. Most of the time it's just once, like we have here, x minus 2 and x. But you can have a 0 occur more often, and then we have another or a higher order multiplicity. Also, I mentioned in the note packet above, so if you look, did you actually look? Probably not, that's alright. So I mentioned that if it's an odd multiplicity, that means that the 0 or the graph will pass through the x-intercept there. If it's an even multiplicity, that means the graph will bounce at the x-intercept there. So what do we mean by that? If I have some graph like this. So this would be odd multiplicity because it passes through this point. This would be an even multiplicity because it bounces there. So that's what we're talking about. Okay, so again, many correct answers if we know the zeros. I could have specified what I want the degree of the polynomial to be. Here we ended up with a second degree to polynomial. This I would not expect you to multiply out. That's a waste of your time and mine. But this would be an 8th degree polynomial. I know that because I add the exponents. Remember properties of exponents? Yes, you do. Okay, so now a few other things about polynomials. End behavior. End behavior, what we're talking about is the graph going up or is the graph going down as the graph goes to the right and to the left. So as x goes to infinity, what does f of x do, or y? Is it going up or is it going down? To determine that, we have what we call the leading coefficient test. It's a lovely little table that relates the leading coefficient and the degree. So what I'm looking for with the degree is even or odd, and with the leading coefficient, I'm looking at positive or negative. So if the degree is even and the leading coefficient is positive, the graph is going to have end behavior that goes up to the left and up to the right. If the degree is even and the leading coefficient is negative, the graph is going to have end behavior that goes down left and down right. If the degree is odd and the leading coefficient is positive, the end behavior is going to go down left, up right. And if the degree is odd and the leading coefficient is negative, the graph is going to go up left, down right. What are we talking about here? So think of a couple of quick examples. If I have f of x equals x squared, the degree is even, the leading coefficient is positive. What does this graph look like? It looks like this. So it goes up left, up right. If I have f of x equals negative x squared, the degree is even, the leading coefficient is negative. The graph looks like this. It goes down left, down right. And then if I have, for instance, let's just do f of x equals x. The degree is odd because it's 1. The leading coefficient is positive. And we know this graph looks like this. So it goes down left, up right. And if I have f of x equals negative x, degree is odd because it's 1. Leading coefficient is negative. This graph goes like this. So it goes up left, down right. So those are examples. That's what we're talking about with end behavior, is you're talking about to the extreme right and left. So it doesn't matter what happens in the middle. It's what is it doing as it goes to the, continues forever to the right, so as x goes to infinity, and continues forever to the left, so as x goes to negative infinity. Possible terms of a polynomial. This is very simple. It's the degree minus 1. What do we mean by possible terms? So terms, most of the time when we're talking about terms, we're also talking about relative minimum and maximum, or relative extrema. It means the same thing. You can see that again in your notes above, if you look. So each one of these would be a term. So this would have 4 terms. That means that it has to be at least a 5th degree polynomial, because the largest possible number of terms you can have is the degree minus 1. So if this is a 5th degree polynomial, it can have 4 terms. It could also be a 7th degree polynomial. We don't know that for sure, but we know that at most it's 5th degree. I'm sorry, at least it's 5th degree because we have 4 terms. Possible real zeros. So again, when we did this example here, these were real zeros. We can have non-real zeros as well, but how do we know the possible number of real zeros? This is just going to be the degree. Real zeros are the same thing as x-intercepts. So this graph here has 4 real zeros. Again, this is possible though. So this has to be at least a 4th degree polynomial. I know it's larger than that because of the amount of terms we have, so it's at least a 5th degree. So that means that there are some non-real zeros in this graph. And again, just to emphasize a couple things on these last 2, is the key word is possible. Okay, so it does not mean that's how many you have. This is just the most you could have. Alright, so tell me everything you can about the function and then graph it. So what do we mean by that? I want to know the degree, the leading coefficient, the end behavior, the possible real zeros, the actual zeros, the actual real zeros, the intercepts, all that fun stuff that's written down. So what do we notice at first? Well, degree. Degree is the highest exponent, so degree is 4. Leading coefficient. Leading coefficient is the number in front of the term with the highest exponent. So the leading coefficient is 3. If the degree is even and the leading coefficient is positive, I know the end behavior is going to be up left and up right. The number of terms. So terms are separated by addition or subtraction, so there are 2 terms. The possible extrema, or number of turns. So if we do possible extrema, which is turns, is the degree minus 1, so that's going to be 3. The possible number of real zeros is the degree, so that is going to be 4. The actual real zeros, how do we find zeros? We solve, or we set the function equal to 0 and solve. So 0 equals 3x to the 4th minus 6x squared. We can factor out a 3x squared. And we're left with x squared minus 2. Set each factor equal to 0. And we end up with x equals 0. Notice that has an even multiplicity. And x equals plus or minus the square root of 2. So those are the real zeros, which are also the x-intercepts. And in this case, all of the zeros were real zeros, so these are actually all of the zeros. And we also conveniently found our y-intercept, because if x has an intercept of 0, then y also has an intercept of 0. Remember, to find a y-intercept, though, in general, you plug in 0 for x into the function. So we found all of the zeros, the intercepts, the possible real zeros, the possible extrema, the terms, the turns, the leading coefficient, the degree, and the end behavior. Now we want to graph this. You have a much nicer graph on your page, so you can use that. I know I have an x-intercept at 0, 0. I know I also have x-intercepts at root 2 and negative root 2. Root 2 is like 1 point something, so I'm going to have a point like here and here. So what is this graph going to look like? Well, if this intercept has even multiplicity and my end behavior is up, up, I know the graph will look something like this. That's not exact. That's okay. That's good enough. And that's showing my end behavior, the zeros, 3 turns in this case, which, remember, those were possible. And just to verify, I can put this into my calculator, hit graph, and I can see that's essentially the picture that I drew. Okay, we'll do the last 2 examples on part 2.